afternoon. We are the AT8 Phoenix, and I am Alyssa.
I'm Adam. Anthony is absent.
I am Anthony, my apologies.
I'm Dakota.
I'm Daniel.
David.
I'm Dylan.
I'm Ina.
I'm Gavin.
I'm Logan.
Okay. Okay, so this is a 3D model from SolidWorks of our final aircraft design. And there's the top view, side view, front view. And as you can see, some of our design choices are the high wing, the T-tail, and 4 propeller engines. Here's the mission requirements. You can see the specifications on the slide, but basically we were tasked with designing a firefighting aircraft to combat the rising issue of wildfires spreading, especially in California. And the main consideration was that we needed to be able to make 4 drops of the fire retardant. And we shot for all the objectives. So we met all the requirements, but we also met most of the objectives so that our plane could be more optimal. The first stage of the design process was our initial estimation. So first we did some initial calculations for weight, and we completed this by separating it into 4 components, which was the weight of the crew, and that was based off a 3-person crew, the weight of the payload, which was based off the 8,000 gallons of fire retardant, the weight of the fuel, which was based on reference aircraft using their fuel weight fractions. And there's an image on the slide showing the mission profile, which was taken into consideration for the weight of the fuel. And then the empty weight fractions, which were based on reference aircraft, which were military cargo / bomber aircraft. And then that gave us a takeoff gross weight of 192,252 pounds. Then for the thrust to weight ratio, this will be discussed further in our propulsion section, but we used the equation on the slide. And this was again based on research and reference aircraft. And of course, for the horsepower, we based it off a factor of safety so that in the event of engine failure, it would function. And we got the thrust to weight ratio for takeoff and landing as shown on the slide. And finally, for our initial estimations, we did wing loading, and the formula used is also given on the slide. And the design wing loading was calculated as 79.3 pounds per feet squared. Again, this was an initial estimation, and the charts on the slide were used, and we plotted our reference aircraft on the slide to get these parameters, such as the takeoff parameter.
So in order to determine our optimal airfoil for our aircraft, we first had to determine the optimal wing loading, or the minimum wing loading that the aircraft would experience to determine the optimal airfoil. And basically with this wing loading value, we could then determine the design coefficient of lift for our cruise conditions. And these cruise conditions were determined from historical data from aircraft for typical turboprop aircraft at 18,000 feet above sea level at 300 knots. And from this, we were able to determine a Reynolds number. So with the Reynolds number, we were able to then search through catalogs of airfoils and narrow down our design coefficient of lift and determine 3 airfoils that best fit our needs. And with those, do more in-depth analysis to determine which would best fit our aircraft. And so between those 3 airfoils, we used software XFLR5 to actually simulate their performance through our flight profile. And we ended up selecting the NACA 643-418 airfoil for our main wing profile due to its high lift to drag ratio at low angles of attack and its high coefficient of lift at low angles of attack. This 6-digit airfoil is optimized for laminar flow at very high Reynolds numbers, which is one of the downfalls of XFLR5. It was the best tool we had available to us, but it is optimized for low Reynolds numbers flow. However, our aircraft is operating at very high Reynolds numbers. So for our actual full wing design, we came up with a wing with a 140-foot span with a 20-foot root chord and a 15-foot tip chord. It has a rectangular planform for 50% of the span and a 25% taper at 50% span. It uses a Horner wingtip to increase the effective wingspan to give us some additional lift, and uses an aerodynamic twist with a 63-412 airfoil, and in addition with that rectangular planform at the root gives us more favorable stall conditions due to the slow flying nature of the plane that it would encounter when it's doing these slow payload drop missions. So in order to size our control surfaces and flaps, we did analytical calculations to determine that we would have the correct roll authority for our ailerons. And then for our flaps, we chose slotted flaps to give us additional lift in takeoff and landing. And then we did further XFLR5 analysis on this full wing to determine that we would be able to generate sufficient lift and be able to calculate our drag values through various flight conditions, simulating the flight at takeoff and landing with various flap deflection angles. And we ended up deciding to mount our wing with 2 degrees angle of incidence to give us a nice balance between different flight conditions for our optimal lift profile.
All right, thank you, Gavin. So after the wing was decided, we moved on to refining our propulsion solution. So initially, we went back and looked over the initial requirements. We also looked at the aircraft mission profile, which was low speed, low range, high loitering times, and then short range. So then we had to select which type of engine we wanted to use. It came down between turboprop and turbofans. Other types of engines were considered but couldn't meet the initial requirements. So the benefits of a turboprop are maintenance, takeoff and landing distances, cost, fuel efficiency. Turbofans excel at range, speed, and altitude. However, these didn't fit the aircraft's mission profile. And then after doing some further research, we found that turboprops are ideal at the design Mach number of around 0.5, which is what we were going to use them for. So after selecting the engine type, we went back to our thrust to weight calculations. We used the same equation that Alyssa showed earlier. This time we used a target thrust to weight ratio of 0.25, which we did some research for. We put in the takeoff conditions, and that got us a couple of different scenarios. So we had to incorporate with 1 engine out. So for 2 engines, each engine had to produce 19,000 horsepower. There's not an engine in production that makes that much power, so the 2 engine layout was eliminated. There is only 1 engine on the market that could produce enough horsepower for a 3 engine layout. However, that had some bad characteristics with stability, aerodynamics, and weight. So we settled on a 4 engine layout because there was more engines available. So then we set up an engine trade study. We looked at 6 different engines. We listed all the required parameters as well as additional ones for us to consider. After reviewing that, we eliminated 2 engines for not meeting the power ratings required, and we put the rest into a decision matrix. After weighting the appropriate criteria, we found the T408 engine was the ideal engine for our choice because of its power, low cost, low weight, fuel burn, and efficiency. So that led us to designing our propeller. We used the equations outlined in the textbook, chose a critical Mach number of 0.8, which is pretty conservative, found rotation rate from comparable aircraft, and that yielded 2 different solutions. In our final design, we utilized the 14-foot propeller. This yielded some thrust generations that are listed there. One thing important to note is the cruise thrust is greater than the cruise drag, allowing us to accelerate in steady level flight. Then for mounting the power plant locations, we considered 6 spots. It came down to the under the wing location because of the clean air for the propellers, and it also disturbed the least amount of air over the airfoil. And then we did a tractor configuration because it was the most efficient and the most common in industry. And then finally, we placed the engine so that way the propellers had at least 3.5 inches of clearance from the fuselage. And then finally, for the fuel system, we did some calculations and found a ferry mission would require 27,000 pounds, and the firefighter mission would require almost double that. We used Jet A1 fuel with a standard density of 6.7 pounds per gallon. And we found that the firefighting mission would require about 6,500 gallons. We looked at the wing capacity, assuming half of the total area could be used. That would be about 20,000 gallons. This was far more than we needed. So we decided on a tank size of 9,600 gallons, so the weight could be more distributed over the wing box and require less material to support it. We're going to talk about landing gear.
Thank you, Dylan. Next slide, please. When it came to the arrangement and the storage of our landing gear, what we came down to was a tricycle arrangement. It's a very common arrangement in the industry. Some aircraft that we looked at were the C-130 and the A400, which also had the tricycle arrangement. It's the most stable of the arrangements. For our specific design, we determined that most likely we would have needed 2 wheels per landing gear and that they would be retractable, which we'll get to in a later slide. And we would be using a pod storage arrangement for when the landing gear is retracted into the fuselage. Next slide, please. When it came to the gear locations, we had to first determine the center of gravity. We designed the main landing gear and positioned it where it would take 90% of the overall load, while the nose landing gear would take only 10%. So per wheel of the main landing gear, we estimated to be about 44,000 pounds per wheel and have to be located roughly 37.5 feet after the nose. And for the nose landing gear, it would be roughly 13,250 pounds per wheel, located about 7.5 feet after the nose. Next slide, please. In the selection of the tires for the main landing gear, we determined that with a 25% load factor, with a load increase, first factor of safety would need about 50.45 inches as our diameter. The only tire, based on the selection criteria that we had, that could fit that design was the 3-part name of 52 by 20.5-23, which has a diameter of 52 inches and a width of 20.5 inches. When it came to the nose landing gear, we based it off of the load of 13,250 pounds per wheel, and we ended up picking the Type 7 40 by 14. Next slide, please. When it comes to general characteristics of our landing gear, the main landing gear rolling radius was 22 inches. The nose landing gear was 18.2. The shock absorber that we're going to be using would be the Oleo shock. It is the most common and most efficient in the industry right now. We decided to have a gear factor of 2.5 based off of the textbook and information that were used based on cargo aircraft and military bombing. So that means that would need to be able to support up to 455,000 pounds. When we came to the stroke length during our calculations, we determined that we could use 7.48 inches, but we added 1 more inch as a factor of safety. Same goes for the nose landing gear with a factor of safety of 9.93 inches. Our Oleo diameter for the main landing gear was 11.5, nose landing gear 8.4. And for our retracting mechanism, we used the 3-bar linkage. As you can see there in the image, makes it simple. And the reason for it is that instead of having 2 axes of rotation where it would then need to rotate inwards, it would simply retract in under about 1 axis into the pods. Next slide, please.
All right, so next up to talk about is the fuselage, tail, and crew station design. So to talk about the fuselage design first, the fuselage geometry depended heavily on the fineness ratio. And the fineness ratio is the ratio between fuselage length and its maximum diameter. To minimize the diameter as much as we can, we went for to try to achieve a ratio of 8 with a diameter of 12 feet. So we came out with a length of 96 feet. Later in our design, we actually changed the fuselage to 12 feet in width and a height of 13 feet. Some other considerations in designing the fuselage was to maintain enough interior space, and this would be for the tanks, the walkways, and the auxiliary systems. Looking at the cross section of the interior space, the internal diameter we have is for 10.5 feet. It's broken up into 3 sections, about 3.5 feet of width each. 2 sections are reserved for the tanks on either side of the fuselage, while 1 section is for the walkway right in the middle. The bottom space is reserved for floor and kneel service area and piping, and the top section is reserved for piping and avionics equipment, both allotted 18 inches. The tank specifically, there are 4 on each side with a total of 8. They're 6.5 feet long, 7-foot max diameter tapered to match the fuselage shape. And then they are gravity operated, and the tanks are made out of clad aluminum. Now we're going to be looking at the tail design. A common configuration is the T-tail, and some pros to the T-tail is that it lifts horizontal tail clear of the wing. It improves efficiency and reduces fatigue. Although this is heavier compared to the conventional tail, the design allows for a smaller vertical tail. For this specific design, the tail area reduction is more advantageous than the lighter weight. So we have a vertical tail area of 436.41 feet squared, while we have a horizontal tail area of 733.46 feet squared. Specifically, the horizontal tail has a leading edge of 85.5 feet aft of the nose with a tail span of 52.39 feet, a taper ratio of 0.56, and a sweep of 5 degrees. While the vertical tail has a leading edge of 90 feet aft of the nose, tail span of 26.25 feet, a taper ratio of 0.65, and a sweep of 16.5 degrees. Now looking at the crew station, one of the specifics of designing the crew station was pilot's vision. And so we calculated the over nose angle was 14 degrees, the overside angle was 38 degrees, and the transparency grazing angle to be 19.15 degrees. Looking at the seats specifically, we came up with a seat back angle of 18.83 degrees, which is higher than the standard 13 degrees. And since the pilots won't be undergoing high amounts of G-force, a higher seat back angle is not necessary. Based on reference aircraft, we will have a 17 degree of sight over the horizon. The crew station design, specifically looking at the cockpit, is composed of 3 crew members. We will have a pilot, a co-pilot, and a flight engineer. The chairs will have the following geometry: a width of 26 inches, the space between the seats will have 29 inches, leg space of 35 inches, head space of 10 inches. And the flight engineer seat is located directly behind the first row and console. Looking at the back half of the cockpit, that we do have a ladder behind the seat-in. This was added to connect to the walkway in the top half of the cockpit. The ladder height is 53.75 inches. Looking at the image on the right, you can also see that we have the bottom half of the cockpit. We reserved this space for additional equipment.
Good afternoon. So for the VN diagram, we use the VN diagram to find the actual load and load distributions on the wing in order to determine the lowest and highest maneuverability limits of the aircraft. So our max load factor of 3.15, we determined that using the dynamic pressure from cruise, as well as the max lift coefficient and the wing loading from landing. While for the min load factor -1, we found that using the dynamic pressure and wing loading from landing, as well as the minimum lift coefficient. And as you can see on the graph, we represented this using the stall speed, the maneuvering speed, the cruise speed, and the dive speed. So our fuselage structure consists of, it is a semi-monocoque structure, and it consists of 9 formers, 120 stringers, 4 longerons, and we also placed bulkheads on both ends of the fuselage in accordance with, like, it replaces formers where it receives large loads. And the way we consider the material is that we consider 3 important factors: the strength to weight ratio, which accounts for fuel efficiency and higher potential payload capacity, as well as we considered fracture toughness, which considers high fatigue resistance through thousands of cycles. So for the material of the skin of the fuselage, we considered 2024 T4 aluminum alloy, which basically we considered it over its shearing properties. And the interior structural components, we consider to have 7075 aluminum alloy because it is less heavy than steel and it is also better cost than carbon fiber components. For the wing, we have a semi-monocoque structure as well. It consists of 33 ribs, which was evenly spaced out to keep structural strength throughout the airfoil. So while loads are being experienced. We also have a I-beam spar near the quarter cord of the wing, which ensures maximum stability and stiffness. We also have 104 stringers placed along the wing, which provides extra axial strength and prevents buckling. And for the skin of the wing, we also use 2024 aluminum alloy. And we also use, for the interior structural components, we also use 7075 T6 alumina alloy.
On to weight estimation and the center of gravity of the aircraft. So as for weight estimation, we found the total aircraft weight to be 186,855 pounds, using the components that we have listed on the right, which were mostly for the structural components found using the textbook Aircraft Design and Conceptual Approach, where the equation listed how to find the weight of each item with respect to cargo and transport aircraft, which is what we classified ourselves as. And so the empty aircraft weight was not including the fuel retardant, was found to be 59,144 pounds. And so we additionally included a weight allowance of 1,800 pounds, which is 3% of the empty aircraft weight, to account for creep and repairs throughout the aircraft's life. Additionally, we found the fully loaded aircraft initial center of gravity 27.27 feet from the nose. This was close to our initial center of gravity estimation, which was 26 feet from the nose. So our aerodynamic center of the wing, which is 26 feet. And as you can see on our right, our center of gravity envelope goes from 27.3 all the way to 28.2 feet. And so our payload mission center of gravity was the foremost, 27.3 feet from the nose, and aftermost, 27.8 feet from the nose. And our ferry mission center of gravity was 27.4 feet from the nose and 28.2 feet from the nose. And this was found using the summation of moments over the summation of weight. And those were plotted on this graph here for 8 different sections, with takeoff with landing gear up, takeoff with landing gear down, the 4 drop sections with the tanks emptying more after each time, the landing with the gear down, and the total empty aircraft weight. And so that summarizes the center of gravity on stability.
Thank you. So after we got the center of gravity and weight estimation, we were able to do a static stability analysis on our aircraft. So we found these values based on the center of gravity at the different conditions. We calculated stability for takeoff, cruise, and landing conditions. And we computed these moments about the center of gravity. So for the longitudinal stability coefficient, we would like it to be less than 0 to be statically stable. The value was found using lifting force due to the wing, horizontal tail, fuselage, and also the normal force acting on the propellers. You can see the values that we got from this analysis in the table on the bottom right of the slide. And we also compared these values to reference aircraft in that graph above the table. And based on that result, we felt that these were appropriate for our aircraft. Directional stability was a very similar analysis using very similar forces produced by the wing, vertical tail, fuselage, and the propellers. But we would actually like this to be greater than 0 for it to be statically stable. So in that table in the bottom right, you can see it on the bottom row, the directional stability was indeed greater than 0, and therefore the plane is statically stable for that direction. For the lateral stability coefficient, we again want it to be less than 0. And this was purely due to the wing and vertical tail. And in the middle row of our table, you can see that those are also less than 0. So based on the longitudinal stability calculations, we can compute the static margin and neutral point for our aircraft. And the point of this is to give us an additional security measure to ensure that our aircraft is longitudinally statically stable. Our static margin was found to be a positive 9.91% of the aerodynamic chord, which is appropriate for our transport type of aircraft, which typically has a range of 5 to 10%. The neutral point, which can be determined from the static margin using that equation, was determined to be located 11.2% of the aerodynamic chord aft of the center of gravity. It is aft because the static margin is positive. And this results in the neutral point being located 2.24 feet aft of the center of gravity, the initial center of gravity, that is. And the neutral point being aft of that center of gravity ensures that we have a longitudinal statically stable aircraft. We also did a trim analysis and right now, straight and level flight. This was done based on, again, a moment about the center of gravity. We computed it at the conditions of cruise, takeoff, and landing, and we used those angle of attack values to create this linear analysis in which the goal was to get that value of the coefficient of the longitudinal moment coefficient about the CG to be approximately 0. And doing that analysis, we got the elevator deflection shown in the table, and there is no rudder or aileron deflection for straight and level flight trim. For a crosswind and engine out and trim analysis, this is a worst case scenario that we also wanted to ensure our aircraft was able to sustain. Those elevator deflections that you see for takeoff and landing, they are the same as the one on the previous slide. So for the crosswind section, we defined that as a side slip angle of 11.5 degrees on either takeoff or landing. And we found the values shown for deflection of rudder and deflection of the ailerons. They are a little high for the deflection of the ailerons, but again, this is a worst case scenario, so we believe that these are appropriate. For the engine out trim angles, we defined that as having both engines on one side of the aircraft out. We, based on reference aircraft and the textbook we were referencing, we assumed aileron deflection during this situation to be 0 for a trim situation, because there is assumed to be 0 side slip angle in this situation. And we calculated the deflection of the rudder. And as you can see, they are relatively small. So if there were to be some amount of side slip angle for this engine out analysis, we would be able to, our control surfaces would be able to function to compensate for that.
All right, now onto performance analysis. So the first factor we found was the range. So we did this using the Brugel range equation, which it takes the integral of the instantaneous range. It's not the most accurate, but it's much easier to do. It makes the assumptions of constant velocity, specific fuel consumption, and lift over drag. For the maximum ferry range, we got 5,496 nautical miles. Now this number is a bit high, but this is because this is the maximum possible if we use the entire fuel tank. And since we have a high fuel over empty weight ratio, the practical mission range we got was 1,162 nautical miles. And the reason that's practical is because there's several factors that could change how this is interpreted based on changing velocities or when the drops are performed. We also found the ferry endurance to be 20.2 hours and the mission endurance to be 4.4 hours. This was found by dividing the range by the cruise velocity. Next, we found the balanced field length, which is the shortest runway required for a pilot to, if they're gonna decide to take off or brake in the case of a failure. In this case, we assumed it was one engine failure. And we also added an additional 35 obstacle clearance for FAR 25 requirements. We did this at 2 temperatures at 35 degrees and 35 degrees over an average day of 85 degrees. And this was found to be 4,558 feet for the lower one and 5,344 feet for the upper one. Lastly, we found the operating envelope, which defines the speeds that the aircraft can safely fly in based on the varying altitudes with changing pressure and density. This is made up of the stall limit, the dynamic pressure, or a Q limit, and the absolute ceiling. The stall limit is the lower limit on the graph. It defines the point at which the wing cannot create enough lift to hold up the plane. This is based on the wing area and the coefficient of lift primarily. The upper limit on the graph is the Q limit, and this is based on the VN diagram, the upper limit that we used for that, which was found at 10,000 feet. We extrapolated that to different densities at varying altitudes. And the absolute ceiling is also known as the excess specific power limit, which forms the top of the graph. And that's the point at which the engines cannot produce any more power, enough thrust to propel the aircraft. Based on the upper limit, we decided to make the service ceiling 40,000 feet. While it can technically go higher in some scenarios, we decided for safety reasons to cap it at 40,000.
All right, guys, let's wrap this up with our cost analysis. So for our cost analysis, we use the DAPCA4 cost model. It is a widely used model to overestimate aircraft acquisition costs based on Department of Defense data. And this model is used for cargo aircraft and tanker aircraft and for non-stealth transport aircraft pretty much. And so basically this uses a series of equations to estimate material costs and man hours to establish a predicted cost, which is then ratioed by an inflation factor to a specific year's constant dollar, so we can estimate the cost in the future. On the bottom left of the screen, you can see some examples of some of the equations we use. So basically you find the hours with some constants you have for the aircraft. And then with those hours, you'll multiply it by wrap rate. And that rate includes salaries for labor, overhead costs, benefits, and all of that. The constants we used for our model are our empty weight of 60,000 pounds, our maximum velocity of 400 knots, our lesser production quantity or number to be produced in 5 years, which we use a number of 50 because we assumed we make about 4 to 10 planes per year, and we are estimating this plane to be in production in 2030. And also for our total number of flight aircraft, we used 4. So for producing 50 aircraft, we have our table here. We calculate the hours for our engineering labor, tooling, manufacturing labor, and our quality control. And then these are all multiplied by our rates to get our 2022 cost in millions of dollars. And our developmental support, flight tests, manufacturing materials, into production, and avionics, you don't calculate the hours for those just because that's kind of acquiring materials and acquiring hardware. And so we can divide this up into 2 categories: research development, test and evaluation. And that comes to about $4 billion. And our flyaway cost, which comes to about $740 million in 2022 dollars. And so here with our RDT&E category and our flyaway category, we have our 2022 costs, and then estimating that to 2030, we have a higher number at about $880 million for flyaway and about $5.3 billion in 2030 dollars. As our quantity increases, our price per aircraft decreases. So you can see here, we make 10 aircraft, it'll be about $400 million, 25, $220 million, et cetera. And as far as our maintenance cost, this is accounting for our fuel, oil, and brakes, so consumables, our crew, maintenance materials, depreciation, and insurance. And per flight hour, we have our costs to the right. And then assuming 1,200 flight hours per year, we have our estimated running costs of $20 million in 2022 dollars. So we can estimate that or compare that to aircraft on the market today for an accurate estimation. And with that, that ends our presentation. And if you have any questions, we're going to kind of do like a Q&A. We'll come up and answer questions as you have them. Thank you.
Thank you. Great job. So let's ask our sponsors first if any question from our audience.
So this is Rick Miles from Northrop Grumman. I'll start level, and we can start with your cost, right? So how would you, so you did those costs, and there are other aircraft out there currently, right, to fight fires, right? You're trying to identify a niche market that to go after. That's $738 million a copy. How does that compare with other potential planes you would be competing against?
So it's difficult to say because currently there's no firefighter specifically built plane in the super heavy category of 8,000 plus pounds. All the aircraft that operate in this range are DC-10s that have been converted. There's a 7.4. So they're just old commercial planes that are retired and converted over. So it's hard to kind of compare apples to apples. However, we did some market analysis in California, across the US, and then across the world as well. In California alone, they have over 60 firefighting aircraft, with 15 of those being in the category our plane would compete in. And then, yeah, the United States itself has over, I think, 250 of them. Does that answer your question?
No. So how does 138 million compare with what you would go buy another plane for from another company?
My apologies. So a DC-10, which has a little bit more ability than ours, is over $200 million a plane. That kind of depends on the condition it's in and also the retrofitting. So we, in the super heavy category of the 8,000 plus pounds of fire retardant, we would be the lowest on the market.
You'd be the lowest on the market. Okay.
It's a very small market. There aren't too many planes that compete in there. And we're the first plane that was really designed for this purpose. So we're able to make it efficient and then save costs where we can.
Okay, and then the life of the aircraft versus how often you would need to send it in for periodic depot maintenance. Could you address those two numbers?
Yeah, so are you asking for like the maintenance schedule?
Yeah, kind of talk a little bit to what you expect the overall life of the aircraft to be, and based off of that, how did you go about determining what the maintenance would need to be on the aircraft from a commercial aircraft in general go through periodic depot maintenance in order to make sure that you're keeping the plane up to spec, right, to fly. So could you just kind of address your general approach there?
Yes, so with our limited capabilities to run like FEA and more in-depth analysis, we estimated for the cost, especially for the depreciation, that the aircraft would last 20 years. That's an incredibly conservative estimate, especially due to the simplicity of our plane. I know other commercial aircraft can last over 30 years, especially with the limited number of flight hours we would complete each year. So right now, for cost purpose, it's 20. If we had the capability and resources to do more extensive analysis on the airframe and wing structure, we would most likely be able to, with a high degree of confidence, extend out the aircraft life. Right now, it's just set for 20 years for the depreciation that goes with the unit cost.
Okay.
Does that answer your question?
So it does a little bit, but then I'm going to pull on a thread there, right? So you talked about it should be based on the number of, you're flying 1,200 flight hours per year, but those flight hours are pretty intense when you're actually in the firefighting arena, right? As far as what you're going to need to do in order to go in and dump the firefighting foam and to be effective at putting out those fires. So I would think while if you were just flying 1,200 flight hours, without going through those sort of maneuvers would be good. But the fact that you've got to get down close in order to be effective at extinguishing the fire, I would expect some of those cycles to be a little bit more brutal on the aircraft. And so 1,200 flight hours per year, it's more how many cycles are you going to do of that firefighting mission?
Yes.
More than the actual flight hours.
The competition gave us for the maintenance cost to assume 1,200 flight hours. It didn't give specific ratios, but it did say to consider firefighting missions, which are harder flight hours, ferry missions, and then also training missions. We estimated that about 60% would be firefighting missions, 30% would be ferry flights, and then 10% would be training. Like I said, we don't have the capabilities to really simulate properly the stresses the airframe would experience in a firefighting mission. We couldn't find that data online. We assumed that it would degrade the aircraft about 20% faster than just a normal commercial aircraft going through pressurization cycles. And that would result in.
Normal aircraft traditionally do major maintenance cycle checks around every 100 flight hours. Because their aircraft is going through such heavy flight testing and like flying activities, it would probably be closer to once every 30 to 40 flight hours if I had to estimate.
Okay. Overall, I thought y'all did a really, really good job with your presentation. Just wanted to bring up those things to think about a little bit.
Thank you so much. Yeah.
Thank you.
Thank you for the question and the feedback. Any other question?
Yeah. Am I allowed to ask a question?
Yeah, of course.
Okay, so I've been a little distracted because I've got a lot of other stuff going on. But so you might have mentioned this, and if you did, just we can skip it. But you guys have all seen the movie. This probably isn't appropriate. We're recording, right? I'll say it anyway. You guys have all seen the movie Die Hard, the greatest Christmas movie ever,
Yes,
right?
sir.
In the end, where the character Bruce Willis plays basically punches a hole in the fuel tank of an airplane with the bad guys on it, and as the airplane is taking off, it leaves a trail of fuel behind it, and then he opens up his lighter and says yippee ki and throws a lighter onto the fuel, and the plane blows up. so you guys are basically doing a yippee-ki-yay moment like every time you take off, right? Like you're going to fight fires. So I'm wondering, what you've done to prevent situations just like that, where you get like a puncture or something in your fuel tank and you're literally raining like jet fuel down on the fire. How do you harden the plane and prevent that from happening?
So I can speak, you want to go ahead first, Gavin?
Yeah, so well, traditionally fuel tanks will be self-sealing if they're like in combat situations, so they can withstand bullets or any shrapnel that impact them. But for a firefighting scenario, that's not exactly the case. We're not expecting to be like going under any fire of shrapnel or lead of any sorts. But our fuel system is completely separate from our actual retardant system, and like they undergo a different like refilling every time the plane lands.
We did also originally design the fuel tank to comprise 90% of self-sealing fuel tanks. We got some feedback kind of questioning that, saying that usually self-sealing fuel tanks are reserved for military aircraft and combat, and it did add a significant chunk of weight, so we did remove them.
If the fire fights back, we can add those back.
Yeah, however, if further testing shows that that is a critical component, we can add them back as well.
But the fuel tanks are embedded in the wing structure, which kind of adds an additional factor of safety. Whereas if you get like a puncture, it's all split up into individual chambers, so you'll only lose a small portion of your fuel at a time. You won't actually drain all of your fuel.
In addition, we can change the thickness of the aluminum on the wing to be thicker to help prevent such punctures from happening.
Okay, awesome. And then my my next question is, what keeps you up at night? What do you, again, we're recording and I'm going to say something that's inappropriate, but how does this plane crash, right? Like what are you guys most worried about? What's the preeminent failure mode?
Well, there's some terrifying videos of firefighting planes hitting really extreme updrafts and their wings just folding in half. So that's part of the reason why we have such a thick airfoil, so we can fit a really thick spar in there. That's the biggest fear. The thing just goes right into the fire with the whole plane, I'd say. But I think we've built it so that won't happen.
Mhm.
If I may say, sir, I don't, and personally, I can't speak on behalf of the team, but I know we put in much work into this aircraft concept, and nothing keeps me up at night in regard to this aircraft. I'm very confident in it.
Thank you, Anthony.
Yeah, good answer.
Yeah, set the bar high.
All right, well, that's it for me. Thanks.
Thank you so
Thank you.
much.
Thank you.
Thank you for the super cool questions, Donald Trump.
That's what I'm known for. I didn't ask these guys the entropy question, but that's probably not fair to ask. So I'm gonna ask the last mechanical team that question. I do it every semester.
Nice.
That'll be it. 4:15 today for those that want to see it.
I am actually.
I will be there. Any other question from our audience?
I will ask one more. So the
Sure.
costing model you mentioned you had a statement there that it's used to overestimate aircraft acquisition cost. I've never seen it presented that way, that it's used to overestimate cost. I'm curious as to, does it estimate how much of an overestimation?
So in the textbook, when it presents the DACA model, it presents a second model. However, it recommended the DACA because built into all the equations that were shown are fudge factors. Basically, the constants we're multiplying by our variables are slightly increased. I don't believe I saw anywhere in the textbook where it provided a specific number, but I believe it's only in the range of about 10 to 15%. So definitely with cost overrun, it's probably not an overestimation, but I think they just build in some fudge factors into the equations to try to account for some stuff.
Yeah, well, because defense contractors are notorious for underbidding and then getting the contract and spending twice what they actually said it was going to cost. So that's the advantage of being in the defense sector versus being in the commercial world. So
Right,
thanks.
absolutely. Professor, how much more time do we have for questions? I just want to make sure we don't run over.
No, just no time limit for question. We can torture you forever.
Oh,
The time limit is your presentation, but for the question section, we can do as long as we want.
Oh, okay.
I'll cancel the rest of the events for my day. Gotta get that answer for the question.
Any other question from the audience? Okay, now it's my turn.
No.
So I want to say really amazing job. You cover all the important topic within 30 minutes and everything present in a very logical way. And in terms of presentation skill and also the slides are very nice to read. Just no like crazy busy slides. I this week, the whole week I saw a lot of slides make me headache. But I'm super glad that the slides you made for this one is like they are super comfortable to read, I want to say. And also the presentation is very engaging, and I really like that. And I think all the key information were presented very well for each topic. So that's my overall comment. And in terms of detail, could you please change to page 11?
Oh.
Why on my screen there's a black thing in the middle, or it's just on my screen?
Oh, that's the messages. Close.
Yeah, close the
that.
comment.
Oh, okay. Which slide did you say?
11.
11.
No.
Okay, so for this one, your choice is a purple one, right?
Yes.
So, and your criteria of selection, this one is a better lift to drag ratio at low angle tach and a higher lift at lower angle tach.
Yes.
I feel like I probably need more explanation, because right now, if I just see the 3 curve, it's not that persuasive that the purple one is much better than the other 2.
Yeah, there's definitely more plots that we could have shown. I was just limiting to 3 minutes. And kind of, I didn't want to spend a whole lot of time going over it, but essentially we did a lot more simulations, like with the entire wing geometry, actually modeling all the different airfoils, because we kind of selected these 3 airfoils, and because all the curves were fairly close together, we actually modeled the wing with all the different airfoils too, and got all the flight characteristics of the wing with the airfoils before we actually selected the airfoil profile first. That was just kind of the time limitations of the presentation of what the graphs that were presented with. But yeah, I agree with you on there that these plots here don't really give that decision a whole lot of justice.
Yeah. So I would prefer that in your presentation, you probably should like emphasize the actual reason why you choose this one. Because now from the graph, let's say, especially for the moment, we want as the angle texture, we want the moment change as smooth as possible, right? And as we can see that the purple one is absolutely not the best option.
Yeah, the one thing to note about that is that the y-axis is really small, like the magnitude.
Oh,
of it is
okay.
0.08. Yeah, so like our actual moment coefficient for longitudinal stability is still very solid, because this, like, with relation to each other, it looks pretty drastic, but overall it's fairly constant.
Yeah. So probably you always need to consider, like, when you do a presentation, when you try to tell the audience my selection is the best, emphasize when your selection is the best. Right.
Okay.
Yeah. So this is this one. And let me see. Page 39. So you guys mentioned that, okay, you chose the 2024 and 7075, and you had a lot of consideration like criteria for selecting these two. I think you mentioned fatigue. What kind of consideration you did for that one?
Say your question again.
So let's say you have different criteria for the trade study of doing the trade study to select the material, and your conclusion, of course, 2024 and 775. What are the criteria you have when you do the trade study for material selection?
So like what we considered for like in terms of selecting material, we based it off like, so there was a couple factors we determined based off of like strength to weight ratio. That was one. That was the most important one we considered.
Yeah.
Because it allowed for a better fuel capacity and higher potential payload capacity. And then the second most important factor we considered was fracture toughness, which basically it needs to have high fatigue resistance through 1,000 loading cycles. So like when we drop the fire retardant, like through like very difficult maneuvers. So that's the importance of fracture toughness. Cost is another important factor.
I will add, in our final report, we have a more extensive table comparing the materials.
Okay.
Currently, not to go over what Daniel said, but we have elastic modulus, shear modulus, density, yield strength, tensile strength, in addition to cost.
I don't know whether to add that or not.
Yeah, so those are all the parameters that we considered. They all were better than steel, and then the two aluminum alloys just had different applications where they were better.
Great. I'm not sure if I heard it correctly. So when you talk about fatigue, you mentioned 1,000 cycles. What is that?
Wait, say, or
sorry, can you repeat it again, Professor?
So when you talk about you consider fatigue resistance, and you talk about the did you mention that 1,000 cycles?
Not 1,000. I said thousands.
Oh, okay.
Yeah.
Okay.
Yeah, I don't think we have a specific.
No, we don't have a specific number for it.
Okay, that's good, because if you say
Yeah.
I'll be wondering why 1,000. So and on page, wait, oh, there's no page number. Okay, your page number stop at 40.
Sorry, you said page 40, Professor?
No, I mean your page numbers stop at 40, and after that there's no page number.
Oh.
Okay, this slide.
Oh no.
How'd that happen?
I can show you how page number on every page. That's one of my comments. So is that the orange one is for the ferry mission, right? And the blue one is for the mission with a payload. And is that there were like several data points. It's caused by the payload drop, change the center of gravity shift. And for the ferry mission, you also have the same data point, but I guess for the ferry mission, you don't really need any payload drop. So what are the data points about?
Yeah, so for the ferry flight, it would take off with no payload. They just happen to intersect, but the reason for the decline is just the fuel burn over the course of the flight.
Those were taken from the same fuel increments that we did with when we had dropped the payloads. It's just to make it more consistent.
Oh, okay. So for the blue one, you consider the payload drop, and for the orange one, there's no payload drop, but it's simply caused by the fuel consumption.
Yeah, it's the same equivalent amount of fuel.
Okay. Now I understand. And you have page number again, 47.
Wait, this one? Yes.
I think I'm 46.
Oh, 46.
Yeah. Because I'm reading the one that you submit on Canvas, so the page number is a little bit different. So I was wondering, when you do this stream analysis, And during the takeoff landing, the deflection of elevator there, the rudder, I understand there's no deflection. And for aileron takeoff landing, there are 0. Why?
We considered straight and level flight to be, well, for takeoff and landing to deal with to not deal with any kind of side slip. And we did do the analysis with the deflection of the flaps. And I think we assumed that was sufficient.
Because normally, especially during landing, we want maximum drag. So we consider all the flaps, including aileron, will be fully extended to increase the drag. And of course, it can also increase the lift coefficient. So maximum lift coefficient at lower speed, as well as the maximum drag to slow the aircraft down. So my feeling that we probably want to deflect the aileron.
Yeah, and that wouldn't affect the elevator deflection whatsoever. It would just be in addition to the elevator deflection, having the ailerons deflected.
You mean with the aileron deflection, without aileron deflection, the trim analysis is the same?
That's what I'm asking. Like so you're saying redo the whole trim analysis with. So essentially, in the equation that we used for trim analysis, we had a term dedicated to flaps. Because we were computing the longitudinal moment about the CG. We didn't consider ailerons because we didn't feel they contributed to the longitudinal moment, but they would be, so
they should.
When you have a positive aileron deflection, right, they're opposite, but when we're landing, they would both be in the same direction, correct?
They're both in the same direction. They are downward, deflect downward.
Right. So how would we report that in the table? Like what, because obviously there's a positive convention for aileron deflection to roll right, but how would we report deflection that's when both are the same direction?
I think the textbook has some estimation method to do that. You can check textbook later. So how this deflection of aileron will change this the trim analysis, everything. So you probably can check textbook later. I just feel it's a little weird that you say that during the takeoff and landing and the aileron is 0 deflection. You know what I mean? Yeah. So check textbook later. And for the, I guess on page 51, this 120 is after the post symposium, the sponsor asked like 35 is not hot enough. Maybe yes, this one. I think my page number is different from yours. So now this 120 is something you add after this poster symposium, right?
Yeah, so what we did for that is we took, because it was kind of strange on the proposal because like the plus 35 degree hot day.
Yeah.
So we kept the number that we did for the 35. And then we also did plus 35 degrees on a average hot day, which we got for like 85 degrees. It was 95? Oh, I think we did 85 for it.
Yeah.
Oh, sorry, that's wrong. But yeah. But pretty much that's like the hottest scenario that I could probably possibly be in, is what we're going with here.
That's great. I'm glad that you guys do that. But did you guys email the air database, the person that in charge of this? I tried, but I forgot. It was crazy week.
So it looks like I'm actually on the board for our national or student-led branch of AIAA. We've been trying to get into contact with nationals for the past couple of weeks for other things. So I did reach out in regards to this competition, but they seem to be focusing on the competition itself and next year's rules. So I
I
could
see.
not get an answer, unfortunately.
I see, I see, I see. That's okay. And next page. So you already have calculated service ceiling here is 40,000 feet. So I think it would be better if you can add this horizontal line on the operating envelope, because if you put that horizontal line there, actually it will reduce the range that your aircraft can operate, right? So it's all about, in the end, what is the envelope that your aircraft can fly. And if it's something that does not even affect the final envelope, it's okay not to put it there. But if you actually put the 40,000 feet, put a horizontal line there, it will change the envelope. So I would prefer that you put a horizontal line on the operating envelope.
Yes, thank you, Professor. We'll definitely update that for the final report.
Yes, I think this is like a very small thing and easy to do. And that's all my comments, and amazing job. And one thing I want to say that is very I don't know, I feel really happy to work with you guys this semester, because you know, the whole COVID thing and everything, and you guys are always very happy together, and I don't know, bring the energy to the class and make everybody feel better. So I really appreciate that. It does make everybody's life better. And
Thank you.
Thank you.
Thank you.
you're welcome. And also,